Hello. This lecture will cover pages 44 through 48 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Nodal Analysis, Chapter 3A, Understanding Nodal Analysis. We're going to start out by looking at page 44. On page 44, Chapter 3, Nodal and Loop Analysis Techniques. These are both very important techniques for engineers. You're going to use these the rest of your careers. We're going to start out with nodal analysis. Nodal analysis is a technique used to solve a particular circuit problem. I want you to note that nodal analysis uses Kirchhoff's current law to calculate node voltages. And you're going to see that as we go through the problems. But I want you to compare that with what you see back on page number 50. On page 50 of your lecture notes, look what loop analysis is. Loop analysis uses Kirchhoff's voltage law to calculate loop currents, where nodal analysis uses Kirchhoff's current law to calculate node voltages. The procedure when using nodal analysis to solve a problem, you'll need to memorize this procedure, but it won't be a problem. You'll get it down after you work the first 3 or 4 problems. But rather than going over this procedure 1 through 6, we're just going to work 4 or 5 problems out real quick here to show you how you use it. Nodal analysis, or how you analyze problems with it. Starting out on page number 45, we're going to look at example number 1. Nodal analysis. For the circuit shown below, solve for the node voltages V1 and V2 and the branch currents I1, I2, and I3 using the nodal analysis procedure discussed on the previous page. So we're going to have page number 44 handy here. The first thing it says to do is label the ground reference node. Well, I did it for you. It's usually this bottom node here. This is all one node, by the way. Electrically, this is all the same point. They just draw it in 90-degree angles just so it looks neat. But I'm going to put a point right here, and I'm going to call that the ground reference. This is all the ground reference, 0 volts. Everything is referenced to this. Since there's 3 nodes in this problem, let's take a look. There's 1 node here, there's 1 node here, and there's the ground node. That's 3 nodes. You're going to need 2 equations. Why? Because you do not need an equation at the reference point. So since you have 3 nodes, you subtract 1 because 1's a reference node. You're going to need 2 equations to solve this problem using nodal analysis. So I'm going to label one of the nodes VA. Now that point is really any point along here, but that's V sub 1 rather. That's V sub 1, and here's V sub 2. That point's V sub 2, that point's V sub 1. So this voltage V1 and this voltage is all V2 over here. At node V1 by Kirchhoff's current law, right here, we have a plus 4 minus I1 minus I3 equals 0. Now notice we know this current. This current we didn't know, so I just called it I1. But I gave it this direction, plus to minus. This current, we didn't know it. I just put a direction down, called it I2, and plus to minus. And look at I3. Doesn't make any difference which direction we assign it, but I assigned it left to right. But if I do, you have to put in the plus to minus. This sign convention we've been talking about, this passive sign convention, this is where you have to use it. And if you don't use it, you're not going to get these problems right. So I put the directions of currents in the way I wanted them. I put the sign conventions in. And now, at node 1 by Kirchhoff's current law, we already got the first equation. Plus 4 minus I1 minus I3 equals 0. The next step is plus 4. What's I1? It's V1 over 2. V1, it's really V1 minus 0 over 2. But since it's referenced to the ground, you don't have to write that in down here. It's just simply V1 over 2. And what's I3? The current leaving. It's a negative. It's negative the quantity V1 minus V2 over 12. Don't forget to put these parentheses in when you do these problems, because this negative sign algebraically is going to get distributed here, and you'll miss that if you don't put this in. Now, why am I putting V1 minus V2 rather than V2 minus V1? Because you put the positive sign over here. This is the most positive voltage because you assigned a direction this way. So it's V1 minus V2 over 12 equals 0. Clean that up, and there's your first system equation. at node V1. At node V2 by Kirchhoff's current law, out here, plus V3 minus I2, or plus I3 minus I2 minus 2 equals 0. Right there. What's I3? I3 is, it's still V1 minus V2 over 12. It's still what it was up here, but it's a plus current because it's coming into the node. But it's still V1 minus V2 all over 12 because of the direction. What's I2? I2 is V2 divided by 6 minus the 2 amps equals 0. There's your other system equation. Look through and make sure you can get this to here and you can get this to here by looking at those points up there. Matrix analysis tells us that this matrix, G matrix we're going to call, this is the conductances, by the way. Remember, one are resistances, conductances. The conductance matrix times the voltage matrix equals the current matrix. You've seen this in math class. I want you to go ahead and use your matrix techniques. V1 is 6 volts, V2 is minus 6 volts. Look at the circuit. Since V1 is greater than V2, the assigned direction of I3 is fine. It's okay. What is I3? Just look back at your circuit. It's V1 minus V2 over 12. It's 1 amp. I2 minus 1 amp. I1 3 amps. I would recommend a quick check at node V1 by Kirchhoff's current law just to make sure that the algebraic sum of the currents equals 0, and it does. I would just make sure at node V2 by Kirchhoff's current law that the algebraic sum of the currents equals 0, and it does. If these are true, then you know you got these right on the test. Just takes a second to do that. Example number 2. For the circuit shown below, derive the 3 system equations in standard form that describe the network. Then, given the values on the next page, solve for the node voltages V1, V2, and V3. Here's a different circuit. I use general parameters here. R1, R2, R3, I sub A, I sub B. There's 4 total nodes there. Take a look at this until you see 4 nodes. There's a node here. This is all a node. This is all a node right here. There's one node. I called it V1. There's node V2 right there. That's the second node. Here's node V3. All this is node V3, V3. And then the ground node. That's 0 volts, but there's your ground node. There's four nodes. Therefore, you need 3 equations. Where do you need the equations? You need equations here. You need equations there. You need equations there. How do you get the equations? Here they are. At node V1 by Kirchhoff's current law, look at node number 1. There's the currents. The next step is here. You clean up the equation and you get that standard system equation. It's the node equation at V1. Look at node 2 right here. Take your time by Kirchhoff's current law. There's the expression at this point right here. That current's coming in, that current's gone out, that current's gone out, and that current's gone out. Based on the sign conventions I put up here. Now keep in mind, I just assign these currents in any directions I want. It usually makes sense to make these gone to ground up here. But this one you don't know. I just assigned it left to right and put a plus to minus. This one, another student may assign it right to left and put a plus over here and a minus over here. You get those directions in and you come up with that third equation, the second equation in standard form at V2, and then you do your node equation at V3 by Kirchhoff's current law. There's the first expression, put in values, and you clean it up. Here's your 3 equations in standard form. If you look at page number 48, there's your matrix analysis of it, taking those equations, those simultaneous equations, and putting it in this form. Now if R1 equal R2 equal 2K and so forth and so forth and so forth, you plug in those values. This is what you should get for your final calculations. V1 and V2 and V3. And keep in mind, since conductance is 1 over the resistance, it's the inverse of resistance. It's much easier working with conductances, G, when using nodal analysis. You don't have to. You don't have to. You can just invert all these and use and come up with, you could go back to these equations right here. Put in the actual values here and get a least common denominator and have all coefficients that are numbers, that are rational numbers, and work at any technique you want to work. I'm just showing you one technique to use your matrix analysis. See learning assessments in the textbook. There's learning assessments E32 and E33. Let's take a look at them real quick here. We're not going to work them out, but I want you to see them here. I don't know how easy it is to see this one right here, but this is learning assessment problem E3.2. Find all the node voltages in the network. Well, all you do to start out here is how many nodes do you have? You have 1, 2, 3, and 4. So you need 3 equations. You need an equation here. See, I labeled that V1. The author did. You need an equation here. I labeled that V2. You need an equation here. I need that V3. And I just assign current directions. I assign this current in that direction, so this is a plus to minus here. I assign this one, this is a plus to minus. You have to put this in. Look where I put I3 down. That's a plus to minus, and then I4 here's plus to minus. And you just take your time. You start at V1. And at V1, at node V1, by Kirchhoff's current law, you write the currents and get the standard equation. Then you do it for node V2. Then you do it for node V3. Now, to solve these simultaneous equations, either find out how you use your calculator to do it by just plugging in coefficients and constants, or there's a really nice application I found with my iPhone. It's free, solving simultaneous equations. And you just plug in coefficients and you plug in constants and push a button and it gives you the answers. If you're going to be behind in working these problems on the exam if you don't have a quick way to solve the simultaneous equations by just plugging values in. So make sure you have some type of application or program that will do that for you. I'll let you use that. And then here's E33, this problem down here. Notice the first thing I did was identified how many nodes I have. Look at it very carefully. Recognition comes with practice, but this is one node here. This is all one node here. I called it V1. Here's V2. This is all one node V2 here. And this is all one node. And I could call it V3, but pay no attention here. Why would I call that V3 when the author always telling me it's V out? Why put in a dummy variable called V3 and then somewhere having an equation V3 equal V out? Because it does. If this is your reference node down here, and it is, you'd put a reference in down at the bottom. Don't call this V3. If it's given by the author as VO, call it VO. So we have a node V1, V2, VO. I assign currents. Just throw the currents in, put your assignments in. I didn't put the passive sign conventions here, but make sure you go through and put, based on the direction you sign the currents, you get those sign conventions in there. Okay? And then just write 3 node equations. Then solve them simultaneously, and you end up with V1 voltage, the V2 voltage, and the V out voltage. They only want V out here. Make sure you can get these answers here on E32 and E33 by solving the simultaneous equations. And once you get all the node voltages in any of these problems, then you can find currents or power dissipations or powers supplied at any element, because you'll have everything you need. And that concludes this lecture.